Binomial probabilities. You should be familiar with the basic notions of probability, including combining events with and, or, and not. It is also useful to know the binomial theorem, its connection to Pascal's triangle, and counting combinations. Finally, the idea of random variables will be used. In this lesson, we will calculate probabilities in successive trials with two options, such as heads or tails when flipping coins. We begin with the simplest case. When you flip one coin, there are two possibilities, each with probability 1/2. When we flip two coins, we use the general counting principle to delineate the possibilities. We make two rows for the outcomes of the first flip and two columns for the outcomes of the second flip. Altogether, we have 4 possible outcomes. Another representation of this process is the tree diagram. Begin at the top. The first coin flip could be either heads or tails, and we follow one of those two branches. The second flip then can be either heads or tails. Since there are 4 possibilities, the probability of each is 1/4. Two of these possibilities, heads-tails and tails-heads, have one head on the 2 flips. If we are interested in counting only the number of heads, we can look at the event 1 head, 1 tail. 2 of the 4 outcomes fit that description, so the probability of getting 1 head and 1 tail is 1/2. We can also list this information using the idea of a random variable. Letting h be the number of heads, we can list the event 1 head, 1 tail as the event h equals 1. When we flip 3 coins, the tree diagram gains 1 extra level. At each step, each outcome splits in half, one string adding an h at the end, the other string adding a t at the end. Notice that the number of outcomes containing a specified number of heads follows the pattern of Pascal's triangle. For example, there are 3 outcomes that have 2 heads on 3 flips. We get this from the previous row. If we already have 2 heads, we add a tail. If we had 1 head, then the next flip should be heads. We can list the probabilities for the event based on the number of heads. Notice that the denominator is 2 to the 3rd power because we have 2 possible choices on each coin flip, heads or tails, so each blank in the general counting principle is filled in with a 2, and there are 3 blanks for the 3 coin flips. The numerators are the numbers from the 3rd row of Pascal's triangle. To find the probabilities for flipping 5 coins, we will need the 5th row of Pascal's triangle. All rows begin with a 1. The 5th row is the row that has a 5 next. Begin with the event getting no tails and all heads, and decrease the number of heads by 1. The numerators are entries in Pascal's triangle, 1, 5, 10, 10, 5, 1. The denominators are 2 to the 5th power, which is 32. In general, to find the probability that when flipping n coins, exactly k land heads, the numerator will be found from the nth row of Pascal's triangle. Here again is the example when n equals 5. Because of the symmetry, we can start with either all heads or all tails. If we start with all tails, the leftmost entry is no heads and then counts up. If you prefer, we can count down. There is one way to get all 5 heads. 5 ways to get heads 4 times, 10 ways to get 3 heads, 10 ways to get 2 heads, 5 ways to get 1 head, and 1 way to get no heads and all tails. The denominator in each case is 2 to the n. The numerator is the kth entry in row n of Pascal's triangle, which is the number of combinations of size k from a set of size n. It is also referred to as n choose k, which is the binomial coefficient. Here's an example. What is the probability that we will get 5 heads in 7 coin flips? We will need the 7th row of Pascal's triangle. From the left, the entries are 7 heads, 6 heads, 5 heads, so the numerator we need is 21. The denominator is 2 to the 7th power, which is 128. The probability is approximately 16.4%.